Welcome back to AP Physics. This is a review summary of Kirchhoff's laws. Kirchhoff's laws are basically tools to be able to use in analyzing any circuits. Oftentimes they are applied to more complex circuits when your normal series and parallel are not easy to apply. Okay, but Kirchhoff's laws even apply to normal series and parallel. Junction rule and loop rule. Junction rule basically says whatever goes in one side comes out the other side. So whatever current flows in one side. So on our diagram here, if I have a current I1 flowing in here, that means coming out of the junction, my junction would be right there at that location. So then on this side, I would have an I2. On this side, I would have an I3. And then I1 must add up and match the sum of I2 and I3. In numbers, if I let I1 be 10 amps, then maybe I2 is 3 amps and I3 is 7 amps. So 10 went in and 10 came out. By the same idea on our circuit that's a little more complex down at the bottom, if I have 10 amps of current being pushed by the battery, then 10 amps go through that resistor, but when I get to the junction right here, it's going to split. Maybe 4 amps go that way, 6 amps go this way, but it has to add up to 10. When those currents join back together over here, it has to still equal 10. So you're not losing charges anywhere. How those amps split up depends on how much resistance is in the branch. So then when we come down to the 3 in parallel, I have 3 different paths. Electrons can't go to 3 different places at once. So I'm going to have some that go there, some that come here, and some that go here. But it's going to have to add up to 10 still. So maybe 2 amps, 3 amps, and 5 amps. And then when they join back together here, it has to add up to 10 amps. And when it returns to the battery, 10 amps. So the total coulombs per second, the total amps being pushed at any point in the wire, okay, around and through any junction has to add up. So in this case, I just arbitrarily chose the value of 10. On your loop rule, the sum of the changes in potential around any closed loop must be equal to 0. So then our batteries here, and I'm just going to use V's, V1, V2. So making note of high potential and low potential. There's high potential plate, low potential plate. Similarly here. And then we would have a resistance value here and a resistance value there. And so then the voltages across these would be an I'm going to call R1. And then over here, this voltage would be an R2. So if I complete any closed loop around there, there's only one closed loop. I'm going to arbitrarily pick a point. We'll go right there. And I'm going to arbitrarily pick a direction. I'm going to go that way. As I go around that way, I am going to make an assumption. I'm going to assume a direction for the current. I'm going to assume that the V1 is dominating, and so my current is traveling in that direction. So then, as I go from my pink dot through the first battery, that would be an increase of V1. As I work my way around, so I've gone to here, now I'm working my way around to there. Now I run into that resistor. That resistor charges flow from high to low. So as I move from left to right across that resistor, I'm going to decrease the voltage by an R1. And then I continue to wrap around, and I go to here, and I get to R2. Current flows from low to high, or high to low. And so that is also going to be a decrease of IR2. And then we continue to move around to the second battery. Now this battery, I'm going from the high side to the low side. So then that would be a decrease in volts of V2. I've accounted for all the voltages in the closed loop. And so my total would be 0. Applying it to the more complex circuit below, and I'm going to use actual numbers here. Let's say that our battery is a 20-volt battery. Well, based on the current, based on the resistances, you're going to have voltage drops as you go through the different resistors. So let's say 8 volts drops across this resistor. Well, I started with 20. I have 8 accounted for, and so now I have 12 left. So then maybe 2 volts are across this one. Well, I have a closed loop right here. And if this is a closed loop, my total voltages have to add up to 0. And so then I'm going to have a 2 volts. Wow. That was a 2. 2 volts across this one, so that if I went around this closed loop, say from here, working my way around, that would be a -2, coming around, going this way. Now this would be a +2. -2 and +2 would give me 0 around that closed loop. Now I continue around the larger loop. I've accounted for 8 volts here. I've accounted for a total of 2 volts here. I don't count it twice because I'm not going on both paths. I'm only going on one closed loop. So I've accounted for 10 of the 20 volts. That means across this, there must be a 10-volt drop. I know it has to be the remainder because there is nothing else left over here that's going to take any voltage. Now, applying that same closed loop logic on the smaller loops in this triple parallel, I would have to have 10 volts across this and 10 volts across this. So my battery supplied 20, and then we dissipated 8 volts in the first resistor. We dissipated 2 volts in the second parallel network, and we dissipated 10 volts in that subsequent triple parallel, and so my total is 0. That's basically what the loop rule is saying. It is just a way to kind of restate conservation of energy, but it's energy per charge, applying it specifically to circuits. Now, where we use Kirchhoff's laws are basically any circuit, but where it's commonly useful is when you're trying to calculate the voltage from two certain locations, A to B in a circuit. It's also useful when you have batteries in different branches, and it's also useful in more complex circuits like RC circuits. So kind of taking these from left to right, I can go on any path in my circuit to get from A to B. I could go across here and down. I'm going to make that a little bigger so we can see it. So I could go across there and down. I could also go across here and down and back up. I could also go all the way around this way and then up to B, and I could make more complex, weird ones also. But any path from A to B is going to give me the same value. So then I'm going to choose the path that is the easiest path. I'm going to go yellow, and I'm going to write it in blue so we can see it. I'm going to follow the yellow path or the yellow brick road, whatever way you want to think about it. So First thing we need to do if we want to find the voltage from A to B is to find the current. Okay, looking at our parallel network there, I have a 12 right here, and I have that in parallel with a 6. A 1 over 6 plus a 1 over 12 equals 1 over R. That's going to be 2/12 and 1/12, which is 3/12. Inverted, 12 over 3. This parallel is going to be a 4. So then I have a 4 and the 5 in series. So our equivalent for the circuit is going to be 9 ohms. Ohm's law, I is V over R. 18 volts over 9 ohms. That's going to give me 2 amps. Now, applying our logic, voltage from A to B on the yellow path, I go through the 5 ohm, that's an I times R for the 5, and I go through the 3 ohm, that's an I times R for the 3. Well, the 5 is pretty easy because we know what the I is because it's in series with the battery. So that's going to be the total current. So that's going to be 2 amps times 5 ohms. That will be a voltage drop because we're moving the yellow line from A to B in the direction the current is flowing. Now, for the second one, IR3, well, we need to find out what current goes through resistor 3. So if we want to find the current there, so I'm going to make a line there, give us some space. We need to find the volts across the parallel. To find the volts across the parallel, I can use I times R for the parallel. All the current, 2 amps, would pass through there if there was a single resistor, which would be a 4 ohm resistor. So then I've got 8 volts. I've got 8 volts on each side. Now, I can't say, oh, I can just plug in the 8 volts for IR3. No, because part of that 8 is across the 3 ohms, and part of that 8 is across the 9. I only need the part that is across the 3. So then I need to find the current in that branch. I3 and 9 would be V over R for that branch. If it's V over R for that branch, I have 8 volts over 12 ohms. So that's going to give me 2/3 or 0.67 amps. So then 0.67 amps go through the 3 ohm resistor. This value is also negative. Combine those, that will get you the voltage from A to B. Now, if you're considering, well, which point is it higher voltage, higher potential, A or B? Current always flows to lower potential. So then A would be at your higher potential. So Kirchhoff's laws, or a fraction in this case of the loop rule, very useful when you're trying to calculate voltages between different locations in circuits. Now, I didn't leave myself a whole lot of room, so we may squish a little bit, but that's okay. We'll put a line here. We'll change colors. It will all be good. Batteries in different branches, second application. So we have our more complex circuit here, and we would be looking at what current flows in each branch. So we have 3 unknowns, a current in 3 different branches. And so we would want to set up 3 different equations. So then looking at our batteries, our biggest battery is 10 volts. And I'm going to put our plus and minus signs in on these so we know what direction they're tending to drive currents. And then we're going to highlight our different currents. I'm going to say the 10 volt battery dominates. So I'm going to go I1 is here and flowing in that clockwise direction. I'm going to put I2 across the center branch, flowing to the left, and then I3 I'm going to put down here in the lower branch. So then our first equation would be just I1 enters the junction right there, and I2 and I3 leave it. So I1 equals I2 plus I3. Now that's our junction rule equation. We need two loop rule equations. We're going to go loop rule on the top loop and loop rule on the bottom loop. So where you start doesn't matter. What direction you go, clockwise or counterclockwise, doesn't matter. What does matter is once you've made those choices, making sure you have the correct signs. So I try to be consistent. I'm quickly using up all my favorite colors here. So let's go purple. On the top loop, I'm going to start right there, and I'm going to go around in a clockwise direction. So batteries, when I hit them going from negative to positive, that's an increase. Resistors, here, batteries from negative to positive when I'm going in my loop that way, that will be a positive voltage. Resistors, when I'm going in the direction of the current, that will be a positive IR. Resistors, when I'm going against the direction, that's a negative. When I'm going in the direction of the current, then your voltage drop across the resistor will be negative. When I'm going against the direction of the current, then my voltage drop would be a positive, because current always flows from high to low. In that context, as I work my way around our loop, so starting from my purple dot, I'm going to go this way, I run into a battery. That's low to high, so then that's going to be a positive 10 volts. Then I keep going. I run into the 8 ohm resistor in the direction of the current, so it's going to be a negative. V equals IR, so that would be I1 times 8 ohms, or 8 I1. Then I continue to move, and I go across the center branch, and I run into a battery. I go from positive to negative, so that is a decrease of 6 volts. Then I keep moving, and I run into the 3 ohm resistor. I am moving in the direction of I2, so then that would be a decrease of 3I2. And then I continue to move, and I run into nothing else. So then my total there of all of those is equal to 0. Then I move to the bottom loop. That's a good color. When I move to the bottom loop, I'm going to start somewhere. So I'll arbitrarily start there where I just put the brown dot, and I'm going to go around in a clockwise direction. So then starting off here, I run into the 3 ohm resistor. Well, the 3 ohm resistor, I happen to be going opposite the direction of I2. So then that is going to be an increase of 3I2. Then I continue to move, and I run into the 6 volt battery. Going from low to high, that is going to be an increase of 6 volts. I continue going, and I go down the lower loop, and then I run into the 5 ohm resistor. I'm moving in the direction of the current I3, so then this would be a decrease of 5 I3. Then I continue moving, and I run into my battery. I go from low to high, so that would be an increase of 4 volts. I keep going, and I made it back to the beginning, and so equals 0. And so there's your system of equations you would use to solve down for I1, I2, and I3. Based on the format of the AP exam this year, it does not look like they will have you doing long math because you have to write out the responses. So then what I would look at in terms of this is the logic of what is going on, understanding the increases and decreases, understanding what directions the batteries are tending to push currents, understanding what is combining in terms of currents, so the overall patterns and the idea. But to solve down a system of equations based on what they have released, it doesn't sound likely that you're going to do that. RC circuits. I have run myself out of room, so we're going to cheat. And we're going to pop this over to a new slide. So, RC circuits. That's another place that you use the logic of Kirchhoff's laws. So, on here, we have a resistor, we have a capacitor. If we're going to use the loop rule to be able to analyze this, I'm going to ponder closing the switch to A first. And then we'll come and close the switch to B after that. So if we close the switch to A, I'm not going to adjust my diagram. You can imagine it's closed to A. If I close the switch to A, then all I have in my circuit would basically be the battery, R1, and the capacitor. So then the loop rule says that the changes in potential will equal out to 0. So then on my battery, high side, low side, I have an EMF. My voltage across the resistor, that is an IR1. The voltage across the capacitor from C equals Q over V. V would be Q over C. And my total is going to be 0. The logic of getting the signs on this one, you can think of what is supplying and what is dissipating or storing. So then your battery is supplying, that would be positive. Your resistor is dissipating, that would be negative. Your capacitor is storing, that would be negative. Now I'm going to write one more line. Positive EMF minus, when we put that resistor in there and that capacitor, you are spreading the charging of the capacitor out over time, which means the current is changing. So I'm going to replace the I by a dq dt. And instead of writing capital Q, which is typically total charge, I'm going to write that as a small q. And this is your differential equation. Now, conceptually, they may ask you to explain the logic of how you would solve this circuit down or how you would set up a differential equation. That is the logic. I'm not going to go through solving it down. It's unlikely you would do that. And there's another video that I posted a couple months ago on that derivation if you want to review that. Now, if we close the switch to B after the capacitor is charged, so after the capacitor is charged, if I throw our switch over to B, then basically our circuit is going to be only the little loop that is over there on the side, and the battery is completely cut off because A is not connected anymore. So then our loop rule equation, when we close it to B, is just the capacitor, Q over C, and the resistor, I times R, and our total is 0. Now, in terms of signs, your resistor is dissipating negative. Your capacitor, this still represents stored energy per charge. And so it's a negative. They're both negative. One more line here. I would go negative Q over C minus dq dt times R equals 0. And again, this is your differential equation that you would use to solve down to come up with a Q of t and then subsequently an I of t equation. So then looking at the overall summary, there are the equations that we have derived down previously for charging and discharging the capacitor in an RC circuit. Now, I want to focus a little bit more on the conceptual side. So on the conceptual side here, when you place a resistor in a circuit, a resistor allows charges to flow. You get a current. A capacitor stops charges from flowing. So then a capacitor stores those charges, and as we said a million times, stores energy because it is storing those charges that are there. So then when you put the two in a circuit together, the resistor allows the charges to flow, the capacitor stops the charges from flowing, so you end up with a situation where charges can flow, but then they get backed up. So you end up charging the capacitor over a period of time. Had you not placed the resistor there, you would charge the plates of that capacitor nearly instantly, which would mean you would have very high current flowing in your wires for a very short period of time, which can be dangerous to the circuits. Okay? Now, in terms of our equations, time constant, tau equals R times C. Well, that R times C is in the denominator of each one of our equations in terms of the base E, keeping in mind that exponent of base E is negative, so then that E would actually be in the denominator of the overall fraction. Looking at the exponent, negative t over RC, in that exponent, the R and the C are in the denominator. So when you make those larger, the denominator of the exponent gets larger. So then your fraction gets smaller. And if your fraction in the exponent gets smaller, it takes the time, the t, longer. You need more seconds to be able to get to the value of RC and to cause that change. So the net effect of changing your R and your C is when you make them larger, you have more time passing to cause the changes in the current and or the charge. So considering our graphs there, charging on the previous diagram when we had the switch closed to A, when you're charging, if you apply by the logic of the equation, CE, 1 minus E to the base E to the negative T over RC, or you think about it conceptually, when you first close the switch to A, you don't have the capacitor hooked up yet or previously, so it's going to start off with 0 charge. As that switch remains closed, charges are going to move, they're going to flow, and that capacitor is going to build up charge. So you're going to approach that maximum amount of charge as an asymptote, and that maximum amount of charge would be CEMF. Current. Think about what's going on with the current. When you first close the switch, there's no charge built up on the capacitor. And if there's no charge built up on the capacitor, those charges are going to want to rush out there. And so when you first close the switch, your current is going to start at a maximum value, I naught or E, EMF over R. And as you charge that capacitor up, then the flow of charges is going to be reduced because you're piling more and more charges on the plates of the capacitor, and they repel additional charges from flowing there. So then you approach 0 as an asymptote. When you are discharging, you know you're starting with the capacitor fully charged, so you can discharge it. So you're starting at that maximum value, CEMF, and as you discharge, you eventually approach 0 as an asymptote. Current for discharging, well, if your capacitor plates are fully charged, that means the charges are most motivated to flow to the opposite region of charge when you first throw that switch. So then your current is going to start off at that maximum value, and as you further and further discharge, there are less and less charges passing, and so your current approaches 0. So 3 of your 4 graphs are identical. It's only the initial charge graph that is different. Now, the difference that different time constants make, I'm going to smash another graph in here, and I'm just going to go for one of these. Because the implications will be the same for the other. So if we deal with our I of t for charging, well, if you have a small time constant, small r, small t, then what's going to happen is you're going to start off at that maximum, and you're going to very quickly drop that current off. If you have a larger time constant, then what's going to happen is it's going to take a greater period of time to drop that current off. So then basically, the larger your time constant, the more you are elongating these graphical relationships. The smaller your time constant, the more you are smashing them together in a very short period of time. So that's an overall summary of Kirchhoff's laws and the predominant applications where Kirchhoff's laws are used.